Our project talks about MPQ Lambda, which is a combination of model-based and model-free approaches. So let's discuss both those in some detail. So model-based approach uses a dynamics model here to generate a sequence of rollout trajectories. So essentially, using a dynamics model, you generate a bunch of action trajectories, normally sampled from the total action environment space. You execute that on the system and collect a bunch of rewards given your cost function. You then select the best action. You select the first action of the best action rollout based on the reward. Now we move on to model-free learning, or in this case Q-learning, a type of model-free learning. In Q-learning, the agent attempts to associate the cost with taking an action at a given state. So in Q-learning, a policy takes a series of actions at a given state, and the state, action, and cost is recorded. These are fed into a dataset. A Q network is then trained on this dataset, so it learns to predict the cost given a current state in an action. Over training, the Q network gets better and better, and eventually the final trained neural network is able to predict the cost given a state in an action. So now we can discuss MPQ Lambda, which attempts to bridge MPC with Q-learning together. So MPC has some disadvantages where if the model is incorrect, has bias due to sensor noise, if the hardware gets old or degraded, it can have a bad prediction. So MPQ Lambda attempts to fix this by fusing the estimates from the MPC, the estimates from Q-learning. Essentially, the Q values estimated from MPC are fused with the Q values from Q-learning through a lambda function. This lambda function decays during training and is constant during evaluation. This was the naive MPQ algorithm that was implemented in the paper that we are studying for this project.
So now we're going to go over our key insights. We know that the MPQ lambda algorithm blends the Q value estimate from the Q-learning network and the MPC dynamics model using a constant lambda. We hypothesized that reasoning about the uncertainty of the Q network at every state and using that to adaptively change lambda will lead to better rewards across the board. So let's get into our approach. First, we learn our dynamics for computational efficiency. This is done with a standard supervised learning approach. To estimate the uncertainty in our Q network, we decided to employ an ensemble network. This ensemble network works by using a multi-layer backbone and k separate heads. Each of these heads outputs a different Q value based on a given state action pair. From this, we can obtain a mean and also a variance. This variance we're using as an estimate of the uncertainty. So now comes our adaptive MPQ lambda algorithm. First, we run the same training loop as MPQ lambda, with the exception of the fact that we are collecting all the variances that are outputted from the ensemble network during the last 1/4 of training. We use this to estimate a baseline mean and standard deviation of the ensemble network variances. During evaluation, however, we update lambda adaptively for every rollout based on the Q variances from the initial state and initial action.
Alright, so we evaluated our algorithm in the Panda Reach environments in both using noise injected into our observation and no noise injected into our observation. And so we did this over 100 episodes with a 50-step max step count, and we essentially averaged the number of steps that the algorithm took to complete or reach the goal. So now we can look at the actual training of our algorithm, starting with the dynamics model. So as you can see, the dynamics model overlaps really, really nice with the ground truth when evaluating it over a 100-step rollout. So now let's look at the actual training of the algorithms, starting with the original MPQ algorithm. There's a reward of -1 for every time step at which the algorithm had not reached the goal. And as you can see, this training was very, very noisy, rapidly fluctuating between 0 and -50. However, it did seem to get a little bit better at the end. Now, in comparison, the training of the adaptive MPQ is much better, with a lot less frequent fluctuations between 0 and -50. So the training process was overall much more stable, with a lot less variance than the previous algorithm. So this algorithm overall had a much more stable training. So now let's look at the evaluation results. So as we can see, the adaptive MPQ and MPQ both vastly outperformed using only MPC, with the adaptive MPQ and MPQ vastly outperforming the MPC only in the noisy environment. In addition, the adaptive MPQ did slightly better in both the noisy and noisy environments, indicating that it was an improvement over the previous algorithm. From this, our key insights are that MPQ and adaptive MPQ perform better than MPC, especially in noisy environments. Ensemble Q networks help stabilize the training process, and adaptive MPQ overall generally outperformed MPQ.